Uh, Good evening, everyone. I am Apurva. I'm a PhD student at IIT Bombay, and I'll be taking the tutorial for Stochastic Control and Communication, week 3 as well. Okay, so are there any doubts from the last 2 weeks' lecture content or assignments or anything?
One clarification I need,
Hmm.
some confirmation. Actually, I was reading book and to get better understanding, I did chit chat with ChatGPT.
Okay.
One line came like there are Markov chains. So each action we consider a separate Markov chain and we combine those, it become MDP. Is that statement correct?
It's a slightly rough statement.
Okay.
Um, the reason being, so do you recall last time, as an example, I had shown an MDP?
Yes, yes, yes.
Do you recall I had shown something like this? In fact, this is from the last week's notes itself. So here you can uh, take the different actions. So here the actions are these, either the red lines or these dashed blue lines. You can take these actions and create two separate MDP, two separate Markov chains. In a sense, that is correct. Putting all of that information together is what you're getting, but it's not directly putting it together. So, like, the structure of putting it together is important. So the statement that you're referring to from ChatGPT, it's a little rough. That's what I'd say.
Okay, okay. And that structure do not define the reward because Markup chain we don't have reward, right?
Exactly. We don't have a reward system. The reward system is added on top of it.
Mhm. Okay.
And in all of this description, so like being able to make such a representation, there's an underlying assumption here. And I'll go through that now. Apart from this, do you have any other doubts?
No, no, not as of now.
Okay, perfect. So I'll quickly recap what we did last time. This is week two's lecture notes. So we talked about the formulation itself. So we started by talking about the stochastic control formulation. There, the core thing was there is a dynamics between how the past state is used to define the current state. Along with that, the past state, the action taken at that state, and some random variable that may have been present, some noise, and so on. All of these together are used to specify the next state. This was one particular formulation, and here the goal was to minimize a cost of this kind. It's a additive cost. The additive nature of this cost is something that becomes important, as we'll see in the upcoming session. Then we said that we are going to mostly talk about the situation where this is a closed loop problem, meaning the actions are actually dependent on xk. They're taken sequentially, and hence they have knowledge of whatever was the realized value of the previous state. Using that, the actions will be taken. There could be different situations. Either there could be Markovian um, type loop, or there could be history dependent loop. These are all the things that we talked about last time also in great detail. Then one of the problems that was discussed was the inventory control problem. We talked about a few different variations that are possible in the same setup, and how all of them can be modeled in almost the same way with minor variations here and there. Then we came to another way of formulating the same problem, which is called the Markov decision process, MDP. So these MDPs are things where instead of having a state dynamics definition of this kind, the definition converts and becomes in the form of probability distributions, as in what is the probability of being in state S and taking an action A and going to some state S dash. Such a probability distribution is defined, which is like a stochastic process, which tells us where the next step will be, which will be the next state, and with how much probability. Then We saw a few simple examples to understand what is what in an MDP, or rather, a simple Markov chain with the sufficient requirements needed. For example, the reward system defined on it, and the different actions for each state defined on it. Then we saw another example. This was a slightly more real world example of controlling a helicopter, and how this actually fits into the framework of MDP, or stochastic control. And finally, we talked about the different types of policies. So today we're going to actually start from here. We're going to talk about these types of policies. We're going to take one example. Uh, I'll change the example slightly from the lectures. So that way you would have seen a few examples by now. And then we'll look at not all of them, but at least the most important ones from this list, the different types of policies. So I'll get started from here. Okay. So, the different names of the types of policies that are commonly seen are first Markovian. Markovian means that starting from the current state S, we go to some action. If the policy is of this kind, meaning dt is a function which starts from S and goes till A, or rather, let me be more clear, A is actually the union of the action space of each of the points in the state space. This is small s, where small s belongs to capital S. This type of a policy is called Markovian. The other one is the history dependent policy. So this is dt, and it takes some history and gives us an action. So what do we mean by history here? So the simplest case would be, again, history is going to be something that is dependent on which time step we are at. So it is something that is h of t. This actually belongs to a space like this. It comes from a space like this. So this is s cross a t minus 1 times. So this is the first time, 0th time. This is at t minus 1 time. And then finally the state at time t. Once we have this much information, that's what we call as history at time t. Meaning, if we want to look at one particular example of it, let me move this a bit more lower. Then we can say, so let's say there's some h1, or rather even h0. So h0 is nothing but the state we are starting out with. So whether that is s0, s1, or whatever it is, the state at time t equal to 0. On the other hand, h1 would refer to state at time t equal to 0, then action taken at that time. After this action taken, what was the state reached? That would be s at time t equal to 1. This is history h1 at time t equal to 1. And similarly, we could write out the remaining history. So a history dependent policy dt of some ht would have dependence on whichever time we are talking about, and it would be just one specific realization of the history. If we are focused on all the set of all the histories, then that would be denoted by capital H of t. Okay. Yeah.
Yeah, I have some like very weird doubt. In
Yeah.
all the policy S to A, there is no constraint of A of S. What if A of S is null set? Basically, some state we don't have any action to do. How do we deal with that? Like, because as of now, I've never seen, even in book and sir also not putting any constraint. A of S should not be null.
No, it's possible. So it could. So if you reach a state where there is no further action possible, that is pretty much a terminal state. You can't do anything further. You've
Only
reached the
terminal
end.
states.
Yeah, not all. See, a terminal state can still be something where there can be a self loop, that you can't go to any other state from there. Once you're there, you're just stuck there. These are the examples that you've seen so far. But no one is stopping us from saying um, it cannot go further. Like there is no further action from that particular state. So that is still a terminal state.
Okay, so if A of S is equal to null set,
Hmm.
okay, there is no action at that particular state once we reach. How
Yeah.
do we define then history?
The history stops there. There is no further steps possible. It just stops there. So that is anyways like a okay. So in the problem that we are discussing so far, in the setup that we have so far, we are saying there is a time horizon, meaning there is a limit when the process stops. Either the process stops naturally, like in the case you were saying, where you've reached a state where there is no further action possible, or you stop taking actions after a certain time steps.
Okay, that decision boundary, decision epochs.
Yeah,
Yeah. Oh,
a
thank
time
you.
horizon, same thing. Okay, so this would be giving us some action. So whatever action it gives us will be some action that belongs to st. It will belong to the action space of st. That's the only thing to keep in mind. Like it has to be a feasible action. Okay, so these are two types of uh, policies. One is Markovian, the other is history dependent. Now, there is another version possible. Here, by default, we were saying starting out from the state or the history of states, the history of whatever has happened, state action pairs, we are just choosing one action. The action choice is a deterministic choice so far in these two cases. Another version that is possible is if the actions are randomized. Instead of taking one action as a result of seeing something either Markovian or history dependent, the action that is taken is with probability half. I'm taking action 1, with probability the remaining, the half, I'm taking the other action. So having a randomization on top of actions is also a way of defining policies, and these types of policies are called randomized policies. So randomized Markov policies would be, so this one is randomized Markov. You're starting out with some state. uh is my screen stuck? Okay, just 1 second. Hello. Am I audible?
Yes, yes, you are audible.
Hmm. But you can't see my screen changing.
Yeah, yes, yes, it's stuck.
Okay. Why did that happen? Okay, let me reshare. Just 1 second.
Yeah.
Okay.
Quick fix will be like restart.
Yeah.
It happens, it happens.
Yeah. Okay. Still nothing is visible, right?
No,
Okay. I'll just rejoin from my other device. Okay. Just
yeah, sure. Meanwhile, can I ask question?
Yeah, of course you can.
Yeah. Uh, like what I understood is this is very good, like abstract topics. But how do we connect with the? Is there any framework or some kind of like methodology? You choose a real world problem and then you break down in a simple piece of info. Connect with this. Do we have a template or it just depend on the creativity of problem solver?
So there are two things here. It depends whether your problem can be mapped to this framework of MDP or stochastic control.
Okay.
The mapping might have creative freedom, but it needs to have certain properties for it to, be able. We should be that we are able to map it to here. So, one example of a very interesting idea that I heard recently was, think of think of graph type problems, and you want to study certain behaviors in graphs. Okay, now instead of taking one state or one node of a graph as a state, like doing the mapping of one node to one state in an MDP, think of the whole graph as just one state of the MDP. And
Oh,
that's the thing, right? The quickest mapping we would think of would be node to a state, and then the choice of
yes,
edges
yes,
sort
yes,
of
yes.
refers to actions. Now
Yeah,
what
very
exactly that
intuitive.
means could differ, but ultimately we can always sort of zoom in, zoom out of the problem. So here, if you think of the whole graph as a state, then change, suppose you're like picking a subgraph from there and then focusing on that particular new subgraph. Now that becomes a new state. How did you go from there to there, with what probabilities, with what kind of behavior? Is that Markov? If that is Markov, then you can have a MDP type structure defined on top of it and then use it to do other things. Um, this similar kind of thought process is used when people talk about games like AlphaGo or Atari games or even chess. So
Mhm.
they map the whole. So for example, if it is chess, they map the position of everything on the chessboard, like the whole thing, to
Whole
just one
64.
state. Yeah, all of that, whatever are the positions of the independent components on the chessboard, all of that is just one state. Moving anything changes the configuration, and that becomes state number two, and
Okay.
so on. So, in a game like chess, it's just that the state space is too large to handle, but you can think of it like an MDP. In fact, people think of it that way.
Okay.
Okay, so
And
there's still two.
second would be like in the industry in which I am, like telecom, here
Mm-hmm.
decision should be very fast, very quick. So because of latency constraints by standards and all those things, we are bound by that. Now in MDP, I was reading that like it is sometimes time constraint, time consuming. Like it has
It
to take some time.
Yeah, that is typically the problem. It's a bit of a resource constraint problem. You don't have you don't have the freedom of getting things too fast too soon. Like the
Mm-hmm.
to get good accuracy, you'll be losing speed. If you want really good speed, you might not be accurate enough. So there needs to be like a trade-off between the two, depending on what problem it is being used in. Okay, now I
Okay.
think I'm able to join again. Ah, yes, finally. Okay, but did you get a satisfactory answer to your question?
For first one, yes.
Mm-hmm.
Second one, I need to explore.
Okay, sure. All right. So far we talked about Markovian and history dependent policies, and both of these were deterministic. The way we have thought about them so far, they're deterministic in the sense that at the end of the policy, we get only one action. Given a state, we are told this is the action to be taken, or given a history, we are told this is the action to be taken. But it doesn't necessarily have to be that way. Another possibility is the action itself could be randomized, meaning starting from some state S, we could have a probability distribution on the actions to be taken. So such kind of policies are called randomized policies. One particular scenario is if we are starting with a state space. If our input is the state space, then it is Markovian. Here, P of A refers to the probability distribution on the space of actions. If we want to talk about individually what is happening to the distributions, then we say that given this DTST policy, this DTST policy basically means policy at state st at time t. What is the probability of getting action? A. We'll come to this in slightly a bit more detail further on. This is the probability distribution. Another version could be again randomized only, but instead of being Markovian, this could be again history dependent. So history dependent randomized policy. Here the input would be the history up till time t. So given this much history, what is the policy that is given out, and from the policy that is given out, what is the probability of getting or taking the action A at time step t. Okay, so now let's take the example that was done in class, and then I'll do a few variations to that. Okay, I'll come back to this portion again a bit later. Alright, so this was the example in class. Here, the reason why we were able to draw such a representation, a Markov chain type representation, is because the reward and the probabilities were both stationary, or they were independent of time. If they were dependent on time, the probabilities that you see here, these probabilities or these rewards, these would have time dependence, and hence this structure will be something that is different at different time steps, and we'll have to have all of those snapshots to move further, or we'll have to write down those exact forms, like what is the time dependence here, and only then we can move further. So for now we are going to be talking about MDPs where the reward and the transition probabilities are independent of time. So let's look at this problem again. So here the state space consists of these two, so it's S1 and S2. As a slightly more real world example, you can think of a factory having a machine that is running every day. So let's say there is a decision to be taken whether to let the machine continue running or to get it repaired. So getting it repaired means it needs to be sent to the repairmen, they do some actions on it, and then they send it back. So in that sense, state 1 is the machine being in my factory, and state 2 is the machine in the repair shop, and the actions are let it continue working in my own factory itself, or should I send it to the factory, should I send it to the repair shop. Now here it's not exactly translating to that, but that's the kind of examples you can think of when you have two state problems. Okay, so here our state space consists of S1 and S2. and our action space is dependent on each state. So since we have two states here, the actions for each of them are as follows. So for S1, we see from S1 there are two actions possible. One action is this one, it's the same action with just some probabilities on top of it, and this is the other action. So the two actions are labeled as A11 and A12. This is just labeling. The way this is labeled is the first index tells us which state it is starting from, and the second index is just a numbering, which state it is or which action it is referring to. And for state 2, there's just one action, this one, and that's a deterministic action actually. So here we have A21. This is the state space, action space for S2. Now, the way this problem is defined, we can already see the transition probabilities and so on. We can also see the reward system and so on, but let's just write it down. So here, okay, for state S1 and action A1, the reward is 5. You can see that the reward is 5 here and here. Then it's not time dependent, but just for the sake of completeness, I'm letting the T be there. Okay. Another state, another reward is, let's say, for this action. So this action A12 doesn't have another branch. It goes from S1 to S2 with probability 1. So this is the only reward that is there. So this is state 1, action 1, 2, and the reward is 10. And the last one is for this action, the reward is given as -1. So it's S2 A21 is -1. And terminal reward here is just whatever is n, whatever is the time horizon of the problem. Terminal reward is just taken to be 0. Now let's look at the transition probabilities. So the way I've written the probability, it says given the state and the action, which state will it end up in, which will be the next state. So if we are starting from S1 and taking action A1, there are two possibilities. It can stay in the same state with probability half. It can go to the other state with the same probability. So this is the transition probability here is half and half, where S, well, we didn't even need to write it like that, is just half for S belonging to any of them. So the next state could be either of them, and the probability, the transition probability is the same. Next is for the other action. Starting from S1, if the action taken is A12, what is the probability, the transition probability for that? And that is given as 1. This one is a deterministic action. So this leads us to state S2. And lastly, this transition probability. This is again 1, starting from S2 with action A21, the next state ends up being S2. So the point of doing this exercise is, if we are given information in tabular form like this, we can draw this Markov type representation, this Markov chain type representation. On the other hand, if this is the kind of representation we are given, we can write out these details and use them in calculation when needed.
Yeah, actually, am I audible, right?
Yes.
So what I did is, in when I listened this class, I made a MATLAB code. What I did is this S2, S1, S2, and A. I have three possible actions. So I made 2 cross 3 matrix for reward, and wherever it was not fitting, I put NA, or maybe not applicable or error or something, some message. Similarly, transition probabilities. Now, what just I realize is, if we go in that way, like whole completeness of a system, we can develop a tool for that. But here we can't develop the tool because it will be very tricky to manage the cases. We don't know, for example, S2 comma A of 1 1 for the reward. It's not present in the system.
It's not present.
But how do we capture that information? That's what, like,
So it's up to you. You can either say that the reward for such states is 0, or if you want it to be a numerical thing, then you can give it to be a reward extremely negative, that tells you that okay, these are actually not feasible, but because I have to put some numbers in my simulation or in my actual calculation, I'm just putting it to be a really large number.
because I correct, but somehow I just want a completeness. For every state connect with every action, and then reward also defined, transition also defined.
That's not always the case. There are situations where the reward is only defined at the very last. So, for example, in chess, if you win at the end, only then there is a reward for that last state of the MDP. For everything else before that, there is no reward. So, the reward is 0. So, it's only at the last that a reward is given. Such type of reward systems are also used. It's very common.
But some state where I can get the other component, some values, maybe some player, like some of the values get out, I can get a reward, intermediate reward, but it's fine. It's, okay, I got the point, but still, somehow I feel completeness would have given a very nice touch up.
I just think it's not needed.
Okay.
Okay, let's continue from here now. Where were we? Right, so let's make a few variations to this example and then repeat the whole process. Okay, this was something that was done in class, so you must be very comfortable with it. Let's make a few changes. Are there any changes in mind that you'd like to try out, or you're fine with this the way it is?
This time I want to do S2 self transition.
S2 is self transitioning. See here.
One more.
Okay, you want one more. Okay, right. Okay, let's do it this way then. Let's call this as A22. Let me give it a reward of 4, and probability of this, let it be half. Okay, with the other half probability, let's do this. Fine.
Perfect.
So here now, let's say the reward is what number do you want to put? So let's put
3 comma 0.5. 3 comma 0.5.
Okay, sure. 3 comma 0.5. So now in my description, I need to add a few things here, right? The first would be the action space of S2 has expanded. I'll add it right here, okay? So you can see things with black are the edits in
Yeah,
the
sure.
example from class. Now, since we've added a couple of more rewards, that also needs to be added. Let's do this. Okay, so there is reward RT starting from state S2, an action. Now there is a slight thing here. Let me put the reward here as 4, else we'll have to define reward in a slightly different way.
Yeah, different. Oh, yes. Got
Yeah.
it.
Yeah, the way we did it in the MDP, the reward is actually defined as our S1, SA, and the next state. We used all of this information. The way it was done in lectures, it was without this next state. It was just this reward. That's why it was same for different next states. So that's why I've changed this particular one. Okay. Alright, let's continue. So this reward is 4. Alright, that's the only additional thing here. Then it's the transition probability. So the transition probability is PT starting from S2 with action A22 and going to whatever state. And it goes to both of those states with probability half. So S is anything S1, S2. Okay, so we've expanded it a little bit. Now we'll repeat the same process as it was done in the lectures. So we'll look at Markov policies. We'll look at history dependent policies. And then same thing but randomized. Randomized Markov and then randomized history dependent. Okay, so we'll go through all of them and see what happens. Okay, so let's start with Markov policies. According to the way Markov is defined, we have a DT. It starts out from the state space and looks at the action space of each of those states and it gives us a deterministic action. So here it needs to do that for all the states in the state space. So here we have 2 states. So dt at let's say at time epoch equal to 0. So it's d0 s1. Now it has 2 options of actions. So it can choose from any of them. Those 2 options are a11 or a12. So let's just say it chooses one of them. And similarly the other one would be, we'd have to define the policy as to what happens if the state that was seen as S2. If that was the case, some action is to be taken there also. Now here again there are 2 options. There is A21 and there is A22. It can take either of them. So let's say it takes A22. Now if we were to continue the process, it's going to be the next step. Now next step will be again defined in the same way. It'll be D1 and the state. We don't care which state we reached or how we reached it. We don't care what action was taken to reach there. We are just focused on the fact that this is the state my problem is currently at. With that being the setting, what is my decision rule? What should I be doing next? What action should I be taking next? That's it. So D1 says that okay, if what you see is DS1, this time you take the action different from previous time. Because all it is saying is at S1 you have the possibility of choosing the same 2 actions as before. So now you choose the action as A12.
But there should be a criteria, right, to choosing this because I
No,
have to. Uh,
this is so right now what I'm saying is just making a random choice. This is just one possibly one policy setting,
okay.
nothing more than that. We can actually enumerate how many possible policies are possible in a particular example. We can do that. Just let's just finish this one and then let's talk about that. D1S2. Again, there are the two choices are again available because we are saying we are at state S2. How we got there is of no concern to us. If we are at that state, we have both the two actions available and we can choose any one of them. Let's say we choose A21. This is just some example of a policy, nothing more than that. Now let's talk about the number of policies, number of such policies possible. So let's say number of policies in two epochs. How many variations can you see?
Sorry, number of policy two epochs.
In two epochs. So let's just say we're only doing two steps and we're stopping two time horizon steps. So two epochs means t equal to 0 and t equal to 1. We're already done. So how many total variations of possible policies are possible here? If I'm restricting myself to Markov and this is my setting.
2 to the power 4, I guess.
Mm. So what you did is you took the number of actions. Since in this particular situation the number of actions are same for both the states, so the number of actions A is 2, so you did that and you took the power of it as the number of states available. At each action there are states available, as in to which state it can go to, and then because this is to be repeated for two time steps, there is that, so this becomes 2 to the power 4. Or you must have seen this in class already. This is AB times 2. Okay, so what I have written here is just one possibility. One of those 2 to the power 4 possibilities.
No, sorry, I was wrong actually.
Mm.
Here, it is going for that functional mapping concept. So we need to think like four actions possible, each of two states, and two times. So it will become 4 to the power 4. Like the functional mapping, because I should go from like range to domain side. So I should consider number of actions per states. I think maybe I'm missing something.
Typically, A is just taken as the action space.
Correct. Here
B
it is 4
action.
because functional mapping, right? So I'm thinking like we have basic simple question. If you forget about formulas, simple
Mm-hmm.
question is how do we map states to action? Each state we have two to four possible actions. Some things we can't map definitely.
No, no. For each action, sorry, for each state, you have two actions. Those two actions might be different. You're never mapping the action of state 1 to the action of state 2. You're never doing those mappings. So you actually have only two mappings for every state. Two
Correct, but
mappings
there
to
is a
actions.
union. But like, if you see the line number like there's a union. So S2 union goes. So total union is 4 and states are 2. So 4 into 2, 4 to the power 2 will be like one time epoch, the functional mapping. And then since I have two time epoch, it will become 4 to the power 2 into 2. So 4 to the power 4. I was wrong, I think.
Okay, maybe I also need to check this. I am not 100% sure on this. Okay, let's
Because
mark
of
this.
union, I think every cardinality will be the add up.
That sounds fair. I'll check this and I'll confirm next time, okay?
Yeah, perfect.
Alright, anyways, so what we have written here is just one possible examples. We can enumerate all the different examples and count and verify if this number is actually true or not. But maybe you can try that out yourself, and I'll also try out, and we can discuss next time. But this is just the Markov policies, and that too we're talking about only deterministic Markov policies. Now the other possibility is history dependent policies. Okay, let's do history dependent policies. In the example that was done in class, it just so turned out that history was not any more informative than just Markovian information, and hence for this particular example there was no history dependent policies that were relevant. Was it history dependent? Yeah, that was history dependent. So let's see for this particular example what happens. Before we even start doing that, do you think you want to make a guess? Will history matter or not?
In this case, yes.
Correct, it will. Because of just adding one extra action for S2, we have changed how we reach any of those states. So for history dependent, policies, we need to be a bit more careful. We need to talk about how we go from the space of histories to the action space. Again, the action space refers to the corresponding feasible action space. So this is union over, this is still union over STs. Okay, that belong to S. So let's think about this. So if we are in epoch 0 or the first situation, then the history is a little simple. The history is just whichever state it is in. So it's either state 1 or it is state 2. Then dt is, sorry, dt just depends on that particular state. So this is pretty much the same as Markovian policy right now for epoch 0. So here it has two options available. It can be any of those. Similarly, sorry, this was D0, that's a typo. D0 for S2 or history at time t equal to 0. Let's say this one is 2, 2. Just some random choice, okay? Now it's the next epoch where things will be slightly more involved. Now there's a complete history to be followed, and there are a few different possibilities. We could be in a particular state and it could have started from a different version of the state. So we need to enumerate all of them and only then talk about it. One second, this is, yeah, we'll come back to all of this. So here, if we want to talk about the full history and everything, so what we'll do is we'll look at the initial tuple, the state and action pair. So initially what we have available is, we could have started from S1, taken action A11. We could have started from again S1 but taken action A12, or S2 A21, S2 A22. These are the possible scenarios, and this is what could have happened after epoch 0 is over and an action has been taken. So this is state after epoch 0, or rather history after epoch 0. Now we could end up in either of the two states, right? We could either end up in state S1 or we could end up in state S2. Then what happens for epoch 1? So what is the state after epoch 1? And we want to write that in terms of the D's. So what we are doing is, it is D1. So this is, let's say, some SA pair. This is the initial information. This is where we finally end up. This is where we finally end up. So similarly, and we say this is another possibility. Okay, so we're enumerating what are these different possibilities. So if we started out from S1 A11, is it possible to land in the state S1? So let's look at the diagram again. Oh, where is the diagram? With A11, both of these are possible. With A12, it is not possible. So if this was the action taken from S1, if this was the action taken, we can actually land up in S1, meaning there is something feasible here, and that feasibility is now, since we are in state S1, both of those are again feasible. So it's a choice between A11 and A12 again. It's a deterministic choice, so one of them. So let's just let it be the first choice. With action A11, we could have also landed up in state S2. Again, now that we are in state S2 and it is actually a feasible state, it is reachable with this history, it tells us that we could choose any action here now. Again, we have two options available, and those two options are A21 and A22. And this particular decision rule could choose any one of them. So let it be this one. Is this okay?
Yeah, fair enough.
Okay, now let's look at the other situation where the action taken was actually A12. If this was the action taken, is there a possibility of staying in state S1?
No.
There isn't, right? It's only going to state S2. So this is actually now infeasible. And this is what we reach. And now there are again two options. We are at state S2 and it is feasible. So there are two options available to us, and it can take any of those actions. So I don't want to bother. I will just take the same action as the previous example. So in short, if I wanted to write down this rule in a more compact way, I would say if I started out with state S1 and I ended up in state S2, irrespective of the action, my decision rule is telling me take the same action after state S2. So that's like a summarization of what we have done. It's not necessarily always the case, but here that's what is happening, and it is irrespective of A. Alright, let's continue. Now suppose our history was such that we started out at S2 and took action A21. A21 is the self loop, right? A21 is this one. So we can't reach S1 from here, so this is infeasible again. But this one is not infeasible. Here again there's an option, so let's take the other action now. On the other hand, if we were to start from S2, take action A22, there was a finite probability of coming to state S1. I think it was half. Then here again there is an option, it's feasible. So let's say what is taken after this is A12. And here let it be A21 again. So this way, I have filled out one possible policy decision rule in all the possible history settings at epoch 1. You could continue doing this, and you can already see at epoch 0 this was a very simple rule. Here it expanded quite a bit, and we had to be very careful in checking if a state is reachable or not after taking a certain action. So, doing this again and again is a very complicated thing, but in principle, it is doable. You could continue doing this for other epochs also. I'll not go into all of that. Fine. So,
Yeah.
we have talked about Markov policies and we have talked about history dependent policies. Now, let's talk about the randomized versions. Okay, before I talk about randomized version, let me ask a question. Here, even though we're not fully clear as to what this number will be, the number of policies, we do know that this is a finite number. If instead of Markov deterministic policies, if I had Markov randomized policies, what will be the number of policies, let's say, in two epochs?
Definitely infinite.
Definitely infinite, right? Because it's so one way to think about this is these deterministic policies form, okay, the set of policies form a closed polytope meaning a closed regular shape, a convex shape, and the extreme points of that shape, these extreme points, these are the ones which are the deterministic policies. Any convex combination of those is what we get as randomized policies. So that's the reason why deterministic policies would typically be finite in number if we are dealing with finite space and finite actions. On the other hand, anything randomized, meaning anything inside the polytope except the vertices, would be referring to uh, randomized policies. So these are randomized policies. Okay, so now let's look at a couple of examples of that. So we will talk about randomized Markov policies first and then randomized history dependent policies. Okay, so here remember randomized policies means we are starting with dt, taking the state space as our input, and we're landing up in the probability distribution on the action space. So it needs to have this kind of a structure. So let's try doing it for epoch 0. So at epoch 0, I think this was the notation used in class. Yeah. So what this means is this is the randomized Markov decision process when we are at state S1, and what we are getting is to choose an action A. Now from state S1, the possible choice of actions here are, there are only two options. There's A11 and there is A12. So whatever probability is being chosen, we just need to choose for one, the other will be by default just 1 minus of that. So let's say this is 0.5, maybe not 0.5, doesn't matter. Let's just let it be some lambda, and this is 1 minus lambda, where lambda is between 0 and 1. If we are including 0 and 1 lambdas, that is actually the deterministic case. So that is the special case of randomized Markov process, Markov policy. Okay, this is only for state S1. We need to specify what happens at state S2 as well. The same thing. In the example that was covered in class, for state S2, there was only one action. So it ended up being deterministic by default. There was no randomization possible on top of it because there was only one action to take. But here, since we have two actions to take, this would be some.
Theta.
Sure, alright, let's call it theta. A is A21 and A22. Again, theta has the same range available, that is 0 to 1, including. Okay, so this is at epoch 0. Similarly, we can define what happens at epoch 2, at epoch 1, 2, and so on. There, the value of lambda and theta could be something else. So this lambda and theta is something which is, you can say, is sort of time dependent, and that's why at every epoch this is changing, and that what is giving us a randomized policy. Okay, so I'll skip the part about other epochs. This is fairly straightforward. At epoch 1 and so on, this could be just repeated, but instead of lambda and theta, it could be just some other values. Or for the sake of completeness of this, this is some lambda 1, some theta 1. And the same thing can be done over and over again. Okay, so this is randomized Markov policies. Since the value of these lambdas or thetas are in a continuous range, the number of randomized policies is infinite. Alright, now we can talk about randomized history dependent policies. So for history, let's start at epoch 0. At epoch 0, there's just no history, right? There's just whatever state it is in. So either S1 or S2. Then we have a probability on what actions to take if policy D0 is to be followed at S1. And again, there are two options. Let me call this some lambda 2, okay? This is for A12, this is for A11. For the other case, we'll similarly have Just like before, for epoch 0, it looks exactly the same as how uh, Markov randomized process would look like. It's at epoch 2 and further, things are going to start looking a bit different. Okay, so to do the same analysis for epoch 2, we can use the same table and add more details as needed. So here we will have to specify the probabilities on the action A. So for state S1, the action available is A11 and A12. For state S2, the action available are A21 and A22. And this is what we're supposed to be specifying finally. Now, same thing, whatever was infeasible in Markov is going to be infeasible even now. So that infeasibility is something that we can already put here. This was infeasible and so was this state. Everything else was not. Everything else was feasible. So now the job is only to put numbers here. We could say, so for example, we could say if this was the history, that at epoch 0 it was in state 1 and the action taken was A11, then the next state that was reached was S1. So now we have defined the exact history as in how we have reached state S1. If we have reached it in that particular way, what action is to be taken next? So let's say we say the action A1 is to be taken next with probability 0.4 and the other action, which is A12, is to be taken with probability 1.6. Similarly, we could say if the only thing in the history that changed was the state where we reached after starting from S1 and taking action A11, then there are again two options available to us, these two, and we could just put the values and get some probabilities here also. Next, for these two states, if action A12 was taken, the only feasible state would be S2. So this is where we'll reach and we're supposed to just plug in numbers here. Similarly, if we were at state S2, the only possibility with action A21 is a self loop, so it stays in S2 itself. This gives us some more numbers. These numbers are not that important. And lastly, if we were starting from state S2 and taking action A22, then there was a possibility of coming in state S1 again, and for that there are two options. So let's say both of those options are taken with same probability in both the states. So this is the full history dependent Markov, one particular example of Markov policy for the example that we have seen so far. One thing that you must have noticed already is that in this way of thinking about randomized policies, we could have a parameterization done. So Here I had some lambda, theta, and so on defined throughout. I could have some parameter lambda t and theta t and have those work out the whole thing. You can see, depending on which one we're talking about, if we are talking about Markov, we need a very specific number of these parameters, these lambda t or theta t parameters. While we were talking about history dependent policies, the number of these parameters that we would require would be slightly higher. So, in this example, we would just require lambda t and theta t. These would be the only parameters required. So, that's just two parameters at each time step. That is okay. On the other on the other hand, here it's already one, two, three, four, five, six parameters required. It's because of the history. Now, six parameters required in epoch 1. If you go to the next epoch, the number of such parameters required would also increase. We can have a different parameterization and hence keep track of that. But you can already see the number of parameters is going to keep increasing quite a lot. Okay, so that is one more way of handling this. Alright, with this we have covered one example different from the class. Then this was the second example in class. If you had any doubts here, I'll go through it again. But otherwise, in the process of discussing that one example in detail, we have covered the subtle points that were important even in this example.
Yeah, sure, you can go ahead.
Okay, so I'll just skip this part. There's nothing much in this, it's the same kind of stuff. Now, next thing that was talked about was complexity of the problem. So far we're talking about different types of policies, different types of policy spaces. Ultimately, we're interested in solving for the optimal policy, and optimality is defined in terms of a cost function or an expected cost, which is this j pi with some starting point. So, if this is the kind of problem we are talking about, uh, ultimately it's the optimal policy or the optimal decision rules which are important. And to be able to find those optimal policies and optimal rules, we need to look at how complex the problem is, how big is the search space, and is it actually feasible to find a solution by calculating this expected value at different policies and then find out, is that even a reasonable way of going about it or not. So, one thing to notice over here is, if suppose we were restricting ourselves to a simple problem where state space and action space are both finite and the time horizon is also finite and we're giving it a number n, then what is the number of policies in the Markov deterministic policy set of policies? So with this one we already discussed in the wake of the example, but let's go over it one more time. So here what we need to talk about is, what are the total number of decision rules?
Before that, going to this,
Hmm.
I had one question. This omega k, right? In inventory problem, we understood omega k,
Hmm.
but in case of Markov, omega k is the transition probability or it's a something else?
It is related to theta. Sorry, it's related to transition probability. So, okay, let me give you a quick recap of that. Let me add a page here. So, remember, in our MDP version of the problem, we have transition probabilities, we have the reward function, we have state and action space. In the stochastic control way of looking at it, we had some xk, or that belong to some state space, some actions uk that belong to some action space. Here I'm not putting the subscript because we never really talked about how we're defining the action space, but never mind. We also had a reward system. Instead of a reward system, it was more like a cost system. I do not recall how was it labeled. So I think it was GK of whatever was the input. So XK, UK, and WK. And WK was the source of randomness for us, the noise or the randomness. Uh, in this way of talking about it, we had one more additional thing, which was the evolution. How would we go from a given state to the next state? And we had some function fk that took us from the state where the state was known, the action uk was known, and the realization of the randomness was known. So this was the dynamics to go from state xk to state xk plus 1. If we knew all these quantities inside, if we knew all of these, we were just supposed to plug it into a function and we would get the next state. But we know that this guy is actually a random quantity, it's a random variable. So the probability of this and its dependence on the choice of the function, both of these together are captured in the transition probabilities, because transition probability tells us, starting from, now I'm going to use the notations that we have in MDP commonly, so I'll use the notation like S, but let's keep K as our time. So starting from SK, taking action AK, what is the next state that I end up in? And I have a probability of ending up in that particular state. So in that sense, there is a correspondence between these two. If you recall, in the inventory example, this xk plus 1 had a very simple form.
Yeah, and from there we derive the omega k distribution,
Hmm.
and here the joint sorry, the mass function will be given.
It will be given, exactly. So whatever randomness was here, this randomness had some probability distribution on top of it. Using that distribution and the form of the function, we could create possibly a transition function as well.
Mhm.
This was the way stochastic control was handled. In MDP, this transition function is something that is told to us or given to us, or it's part of the description of the formulation itself.
Okay. And while calculating the cost, I should consider this mass function, capital T.
Yes. So right now, the way this particular cost function is written, it's in the definition, it's in the setting of stochastic control. In the upcoming lectures, it'll come back in the form of MDP, in the MDP formulation, and there you'll see it'll be written in terms of transition probabilities and so on.
Cool. Okay.
Yeah. Okay. So here, if we're talking about decision rules, our focus is on how many decision rules are possible. So suppose we look at any given action one, any one particular action. For that action, the number of states that are available, as in what are the next states that that action can take us to. So that tells us that the number of decision rules is basically a to the power b, because b is the number of states possible for each of those a's. So it's going to be considering all of that, and then that's the total number of decision rules. And because this is just for one epoch, this is going to continue for each epoch. So the maximum number possible of this guy would be, this is for n epochs, okay? So this is ab to the power n. So I think, yeah, I think you were right in saying in our previous example, a actually was supposed to be 4. So here we had this example, right? mm, where did it go? Yeah. So this, you're right, this was an error. This was supposed to be 4. The total action space has 4 actions, and for each of those 4 actions there are 2 states that can be the next states. So that is 4 to the power 2, and because we are talking about only 2 epochs, that was the times 2. Okay, okay, great. Where were we? Okay, now instead of focusing on Markov deterministic policies, if our focus was instead on history dependent policies or Markov random policies, then what happens? We already know if we are talking about Markov random or history random, the number of such the policy space becomes infinite. So we can't really uh, talk about complexity of that, but we can still talk about complexity of history dependent deterministic policies. So suppose our problem was redefined and we were optimizing over this pi hd. Pi hd refers to the set of policies in the Markov deterministic, sorry, in the history dependent deterministic case. So here our j needs to be rewritten again. So the j would have a form like this. X0 just tells us that what was the starting point. So for each starting point we would have a different value of j tilde rather. So this is expectation. This part doesn't change. This refers to the terminal state or the reward of the terminal state. Then there is a summation from k equal to 0 till n minus 1. Gk of xk, uk, and wk. Here, this uk is something that depends on the history. But even though it depends on the history, the final uk, so there are two things here. This uk is a function of some mu k that depends on history hk, but ultimately this has to lie in the space, the action space of xk. So it has to satisfy that criteria. Because of this minor change, the expectation needs to be not only over the randomness in w, but has to be, oh, it doesn't have to be over this because this part is still not random, this is still deterministic, so we're actually fine. So this is, the only difference is how uk is calculated, and that ends up giving us this as the exact form of the cost. Now let's try to calculate the number of epochs, the number of such histories and everything. So let's try to answer this question. Okay, so now we want to ask, if this is the situation, then what is the size of all the history dependent deterministic policies. What is this guy? So let's take one particular scenario. Let's say there is just one epoch to be considered. When it is one epoch to be considered, or we are talking about the 0th epoch, then nothing really changes. This is the same as whatever was there in Markov. So the number of decision rules are same as before. So that's a to the power b. Remember, a refers to the size of the action space, and s refers to the size of, sorry, b refers to the size of state space. But instead of that, if we had two epochs, for the first epoch we are fine, this is as it is. But for the second epoch, something more is happening, right? This time, okay, let's come back to this. We have histories. Our dt depends on some histories, and then it gives us an action, or rather it depends on the history space and it gives us actions from the particular action space, which means in case of two epochs, the history space would be h1. So let's say h0 is what we started out with, which would have been either s0 or s1, one of these. h1 would be slightly bigger than that. h1 would be something from this space. So the number of such h1s or h2s also, the number would be a times b times b. So there are two states. So there are two states to be considered and one action to be considered. So this is ab square. So this is the number of options that are available at any given action, or those are the number of options that would have affected what state you end up in. So ultimately the epoch would have a to the power ab square coming up. We could take this further and talk about what happens if there are three epochs, or what happens if there are more than three epochs. So up till two epochs we're fine, it's still the same thing as before. So it's a to the power b, a to the power ab square. It's the third term that matters now. The third term would be coming from history h2, which will basically be something that is from the space s comma a covered twice, and lastly there's one more s. So the size of such h2s, size of such histories would be, there are two actions, so a square, and there are three states, so it's b cube. So this becomes a to the power ab cube. And you can write it together, and oh, oh yeah. And seeing this, you can actually go and talk about what would happen for n epochs, and that gives us a number. That gives us the size of history dependent policies for the particular epoch or for the particular time horizons. Okay, so if you try it in general, you would get a to the power b. You'll get a geometric series of this kind: a square, b square, a cube, b cube, and so on till a n minus 1, b n minus 1. Alright, so this is all about the complexity of the policy spaces. Any doubts in this part or anything up till now?
So as you mentioned that deterministic and randomized, that convex L.
Mm-hmm.
So in this case, these many unique points will be available on a particular space,
Yeah,
and then convex combinations of all those things will become that randomized version.
yeah.
Okay, it's actually humongous.
It's very large. It's getting bigger and bigger as we increase the number of epochs. And right now we just have two or three epochs, and this is the condition. And typically, when people actually do these problems and search through the spaces, if they have to look at all of those extreme points also, that feels like it's computationally infinite. It's not in number infinite, but it's way too many to search over. So that suggests that there is a need to come up with smart techniques. Like up till now, we have not come up with any techniques of how to optimize. This is just saying that okay, maybe we could just search over everything and then calculate and then see. But that is not a very feasible solution. That's not doable in practical scenarios also. Here, if we restrict ourselves to, a equal to 2, b equal to 2, and then do these, even then the numbers are very large. Okay, actually, give me 1 second. Hold on. Okay, so with this, we have talked about uh, what are the different types of policies, what is the complexity of those policy spaces, and now finally, we'll talk about the there's one optimality condition, and what does it mean, what is it referring to, and how can the structure of the cost function itself can be used to make the problem manageable. We'll just touch upon those things. Since these were not covered in this week's lectures, I'll not go to much detail. So let's look at the cost again. So the cost function has one term that focuses only on the terminal reward or terminal cost, and then there is a additive term. So the additive term is the reward for any kth state at which some action uk was taken and there was some randomness wk in the system. So this is written in terms of the stochastic control formulation that we talked about. Now there are two things here. uh,
But okay, carry on just to that. But in the initial of today's, you mentioned additiveness, and it will be very important.
yeah,
Is it that same point
yeah,
here?
yeah. So I'm coming to that same point now. So now, before I go to the details of what I mean by that, what is happening here and why is it so important, why this additive structure is so important, let me take an example. This was the same example that Sir also took, and this actually is a very illustrative point, so I'll go with the same thing. So let's say you are focused on a traveling salesman type problem, like how do you go from one point to another, that kind of a problem, finding the shortest path between 2 points. So let's say there is a point a and there's a point b, and there are a few paths available. and so on, for example. Okay, now think of the scenario where we are trying to minimize the distance traveled between those 2 points. Okay, so our focus is on minimizing what is the distance traveled between point A and point B. What is the total distance between those two? And in the process of doing that, we go through a few different nodes in the mean. Here, what is important is the distance traveled from point A to an intermediate point, then from that intermediate point to the remaining intermediate points, and then finally this distance. So here again there is a additive structure. If we are trying to minimize the distance, we are minimizing this overall distance. In the process of minimizing this overall distance, I would have reached a state. Okay, let me add one more path here. In this kind of a process, there are quite a few variations. But when I'm trying to add the distance, all that matters to me is what is the distance between this point, this point, and this point, or this point, this point, and this point. I don't care what was the history. Sorry. Um, or let's go a little bit further. What is the distance between this point and this point? I don't care how I reached this point, or even this point for that matter. So I could have reached this particular intermediate node in two different ways. I could have taken a path like this, or I could have taken a path like this. It doesn't matter what I did. All that matters is here I would have two distances, and all I'll have to do is compare. I'm not saying this is like a greedy approach. All I'm trying to point out is the history is not important. It is the next action that is important. And how the next action is taken is important once you've reached this particular state. So, given a
But
policy,
but suppose the cost, if it is more than one, like the cost numerical value, then multiplicative also will work exactly same, right?
let me make the point about the principle of optimality, and then I'll come to what happens in multiplicative if I'm able to make any comments about that. Okay,
Yeah, sure.
because in multiplicative you could always have a situation of there being a zero somewhere, and everything will just become zero.
Oh, got you.
Right,
Got
there
you.
could be a negative term, like even though we're talking about cost, there could be a negative cost, meaning a reward in reality. That changes everything, that changes the whole scenario. That may or may not be the situation in additive uh, cost that we have.
Yeah, I missed that point. Yes,
Yeah,
yes.
so like that's a very different structure. There is a structural benefit in that also, but that's a different direction altogether. It's not so easy to get into product type problems so simply. Okay, um, right. So one structural point here is it's the choice of action that is to be taken from any state that is very important. And on top of that, how did we reach that state? It could be coming from a dynamics, it could be coming from a probability distribution, both of those are fine. But once you've reached that state, we just have numbers as to, okay, this was one way of reaching, this was another way of reaching, and we have just numbers. This is the additive cost from here, this is the additive cost from here. Next step actually gives us a window as to which one of these two we should choose. We could make that choice right here also, but there are catches. Like, there could be negative costs and so on. In distance, that's not the case. Okay, so this additive structure has one additional point that comes up in the form of principle of optimality. What that says is, suppose the highlighted path that I have here, okay, the yellow highlighted path is an optimal path. I'm making that claim. If that is the case, so it's starting from point A to B and I have a good path. Oops, sorry. So now suppose I focus on this node. This is, let's call it A1. What is the best way to start from A1 and reach B? It's because of the additive nature of this cost function, or distance traveled, or even total time. It's not very difficult to conclude that the same path, okay, the same path itself, just starting from a different point, starting from an intermediate node,
Makes sense.
it's still the best path. Because otherwise, if it was contradicting, then that means there existed a different path for which the cost or the distance traveled was less. Then that would have been our optimal path and not the yellow highlighted one. Meaning, if we have already chosen the best path possible from A to B, we have actually also chosen the best possible path between any intermediate point and B. And this is happening exactly because this is a additive problem. It's happening because of the structure of the problem. The structure of the problem is such that this gk, it depends on xk action and wk. It is not depending on the history. It's not depending on how uk is chosen or how the action is chosen. It's just depending on the action. Okay, and what this means in a more concrete manner, this is the statement that suppose we have an optimal policy pi star, and we are restricting ourselves to Markov decision policies for now. If we have an optimal, and in the path of the optimal policy there is some state xi at some time I, which is actually reachable with some probability. So this xi is just some node. Okay, so in our example, this is a node like a1. So in that case, the cost from a1 to b, or in this particular example from xi to the terminal state, or from time step I to n, which is the same cost, the only difference being the addition is from k equal to 0, not starting from k equal to 0, it is starting from k equal to I. Then this cost, this truncated cost, will get minimized by the same policy. What this actually does is it gives us a way of coming up with an algorithm, and those types of algorithms that follow a structure like this are called dynamic programming. So now, if I were to come back to your question, if I have product, um if instead of this additive cost, this is still additive, okay, let's say this is still additive, but here instead of adding these costs, I was taking a product and then adding all of those products with the terminal cost, then I can't really make this claim, can I? Can I say what will happen to a sub problem?
No, as you mentioned, zero
Yeah,
and
0 or
negative.
-1 would change everything.
Because the product of two negative numbers become positive, so you may see it's a positive reward, but when you go back, it was negative.
Exactly. Variations are possible. So, point being, it's the additive structure that is giving us this type of a optimality condition or optimality principle. This may not happen if our problem is defined differently. For example, if it is products, you'll have to verify it very carefully to see if it'll happen or not happen. Okay, so
Okay, or maybe like in the multiplicative case, I can handle with a log and then I can apply this principle and then see if it is applicable or not. So log of negative will throw me the error like it's not worth it. It's not okay.
yeah, you can think about it that way and see if this optimality principle still makes sense. You understand what the condition is. Now try out different variations that you have in mind and see if it still fits this condition, if the go to cost from any intermediate node till the end is still optimized by the same policy or not. Instead of trying to prove it, try to think of counter examples and see if you're able to create one.
Yeah, sure.
It'll be
And
faster
by
that
the
way.
way, this divide and conquer algorithm, it's similar kind of this thing, or
Divide.
it will be different.
What is divide and conquer algorithm?
For example, it's a binary search. So we sort into increasing or decreasing order. Then we search only half space. If it is not, then it will be in the other half, something like that.
Ah,
So here, I am sure that, for example, there the logic is like if like things whatever I'm searching, it is more than the mid value of my array, then it's definitely in that area. Then I'll go and apply iterative logic. Here, iterative logic is like if I am at my end is optimal, I'll go back, then it has to be optimal.
okay. If you're just trying to draw a parallel, dynamic programming has a parallel that you're trying to say. But if you want
Mhm.
to know if this is divide and conquer or not, I think it is not. Because divide and conquer is a greedy approach, right? You're
Yes.
making the decision greedily at each step. Here, making a decision greedily might not end up giving you additive minimum cost. Right? So, for example, what could happen is I can take an example for this only and show you. This is not DP, okay? This is just an example. DP is something that will be discussed in the next lecture, so I'll strike it out rather. Okay, so let's say for the yellow one, which is what I'm calling as the optimal, these are the distances. Okay, 5, 5, 4, 6. So the total distance is 20 for the yellow path. But maybe at the first step here, before reaching the first intermediate node starting from A, maybe this is A1, this is A2, this is A3. Okay, this is, let's call this B1, B2, whatever is intermediary, let me call them C1, C2, and so on. This is some sort of labeling I've done. Maybe it's very much possible that from A to A2, the distance is just 2 kilometers or whatever, some unit 2. And from A to A3, it's only 3. But what happens is the next part might be more. So you can't make the decision only based on this part. Divide and conquer works for binary search because the array is sorted. Right? Here it's a different structure. So sorting can't be done stage wise.
Yeah, makes sense.
The sorting needs to be done in a slightly different manner. There is some kind of a sorting that will be done, but that will be in a different way. You were in the right path in saying that you could actually start from the back. Right? This particular principle of optimality is saying that whatever is optimal, whatever is the optimal policy throughout, will still remain the optimal policy for sub parts of the problem also. Meaning, if starting from the back, if this is the optimal path, then between the other options, these are the other options, right? These are the other options. So these are the 3 options from the back. This should be the optimal one. Or it may not be possible to do it this way. We need the number up till here for all of these paths, whatever is the next step, and only then we can compare. So dynamic programming is going to take care of these things in a much more structured and proper way. But there will definitely be a way to not necessarily have to look at the whole space, only a part of the space, and the space would most likely keep reducing with time, but how it happens is not going to be the same as exactly the same as standard divide and conquer you see in binary search and so on. Okay.
Yeah.
All right, let's the revise. Oh, okay, I had one more example, but it looks like we have already gone through everything that's needed, so I'll leave it in the notes. If you want to give it a try, you can, but otherwise it's the kind of problem that we've already covered. Okay, so today we started out by talking about the different types of policies. We talked about deterministic policies, either Markov or history dependent, and then we talked about randomized policies, again either Markov or history dependent. Then we took an example. We made some variations in this example from the one that was there in the lecture notes, and then we took examples to understand what each of these different types of policies are. One example of each of these to understand what it means and understand how to write it out. What does it mean? So we started with Markov policies, then we talked about history dependent policy. If we were talking about just the 0th epoch or the very first step, then history dependent is still the same as Markov, but as we go to next epochs, history becomes significant, and then it could be different from Markov policies. In our example that we saw, it was definitely different. Then we saw randomized Markov policies, and we talked about having parameterization done here. And last, we talked about these randomized history dependent policies. So, our example was rich enough to have all these policies possible, and we talked about an example of each of those. Then we did not discuss the example from the class. Then before we went on to talk about complexity of the policy space, we talked about the difference between the stochastic control formulation and the MDP formulation, and we revised the fact that stochastic control formulation has some f some fk, that knowing all these parameters, uk, xk and wk, we would know exactly what the next state should be. But since wk is a random quantity, this change of this random quantity would be reflected in the change of the next state as well. And this can, in the language of MDP, be captured by transition probabilities also, without needing to have wk and fk defined explicitly. Then we talked about what happens to the size of the spaces, size of the Markov policy space, or the size of the history dependent deterministic policy space. We saw that they're quite large already. Specifically in history dependent case, it grows very fast with each epoch, and it becomes almost, it seems like it becomes very difficult to handle very quickly. Then we talked about the cost function, and the way it has been defined, and that because of its additive structure, one property comes out, which is the principle of optimality. And this principle of optimality basically says that we can that if we have an optimal policy, then for intermediary steps, the policy to go from the intermediate step to the last terminal step would still have that as the optimal policy. This is the principle of optimality. We looked at an example, this example of shortest path between 2 points, to get an intuition about what is this principle of optimality. But remember, in a typical MDP, we could have more than one starting point and we could have more than one terminal states. Since there can be more than one terminal states, this optimality condition is actually more general than what can be captured here in this shortest path scenario that we have. Okay, and this is an extra example that if you want you can try it out. I have given the details of the MDP. You're supposed to draw the transition diagram, then list out the different policies. You don't have to list out all the policies, maybe just find out the number of those policies, but write one or two as examples. Randomly pick one Markov random policy and calculate the expected reward. Similarly, go for history dependent policy and try out a history dependent random policy and try calculating expected reward for that. So these are things that you can try and practice on your own and see what happens. Okay, with that I'll stop. If you have any doubts you can ask now.
In this principle of optimality,
Mm-hmm.
uh, okay, somehow I'm feeling that I should know the end result first to get the, like, somehow, I don't know, I need to read more. Like, as you mentioned, like, you already know the optimal path or maybe optimal result, and you go back and check how you can follow that. So, is it fair?
See, okay, so right now we only talked about a motivating example and intuition to understand this. So it's too
Yeah.
soon to talk about the dynamic programming algorithm itself, but we'll come back to that. But on the other hand, directly using this principle where it says, let's say we have an optimal state, it's not directly useful, but it's in a reverse manner that it's going to be useful in coming up with the algorithm, the dynamic programming algorithm.
Oh, okay, okay, okay. Got
In a straightforward manner, it's not talking about existence or how to find the existence of this optimal strategy. It's saying, let's say we have one, then that will be the same one that will be optimal even in the sub problem also. So it's in short telling us that we should first focus on the sub problem. What is optimal there might be optimal in the bigger problem also, but it is not necessarily the case. It's possible that
it.
there might be more than one optimals in the sub problem, but in the main problem there's only one optimal. Situations of
Okay,
that kind can happen.
okay. And why is it only for MD? Why not HD?
Oh, if we're talking about history dependent deterministic policies, then there is a slight catch. The UK has dependence on the history, which makes it slightly more
Okay.
complicated. So we need a
It's,
cleaner
mhm.
motivating example and cleaner way of talking about it, but similar things will follow. It'll come up in the upcoming lectures.
Because it seems like this should be general, like there is no restriction on HD, HRMR. I don't need to see.
It'll come up in the upcoming lectures.
Okay, okay. Thank you.
Yeah, thank you.